he studies in the University of Barcelona. And please, you can start sharing the screen if you want, Ricard. So he's going to present some results about the binary neutron star merger simulations, focused in particularly in the magnetic field amplification. So please go ahead whenever you want.
I think it's, yeah, this and this. Right here. Okay, do you see my screen?
Yeah.
Fine. Well, thank you, Daniele, for this introduction. I'm Ricard Aguilera, and in this talk, I will talk about turbulent dynamo in binary neutron star mergers, which is a work done along by Carlos Palenzuela, Daniele Vigano, Federico Carrasco, and Borja Miñano. But before I start, let me say that everything that I will talk about here can be found in these papers that we have done. So if you feel curious later, you can just take a look at them. Well, let's just start with this plot here. This represents objects that the LIGO and Virgo interferometers have detected through gravitational wave emission. Most of them are binary black hole systems that have merged into another black hole from about 20 solar masses up to 80 solar masses. Normally, they are far away from us, in the sense that they are from 100 or 200 megaparsecs away. But in the second run, something new happened, which was the detection of the gravitational wave emission of a binary neutron star merger, which was this GW170817 event. And this represents the beginning of the multi-messenger era, because this merger, in this merger, they don't even detect the gravitational wave signal, but also they detect an electromagnetic counterpart going from gamma ray to radio, covering all the range of the electromagnetic wavelength. The gamma ray was detected few seconds after the detection of the gravitational wave emission, and the radio was detected 100 days before, 100 days after the merger. And in fact, this is important because it was a kind of a lucky event. As I have said before, most of the objects are so far away from us, at 100 or 200 megaparsecs away. But this event took place at only 40 megaparsecs away. And the geometry was favorable because the jet emission was probably pointing to us. So with this event, there are some things that can be checked. For instance, we can test the general relativity equations, the internal properties of a neutron star, like the equation of state. We can improve the knowledge about magnetic amplification mechanisms. We can also check the production of heavy elements and the electromagnetic counterpart, like short gamma ray burst or the kilonova, which comes from the decayment of the heavy elements via our processes. Or focusing on the remnant, we can study the formation of a hypermassive neutron star or a light black hole. Focusing on the equation of state, knowing the equation of state is one of the biggest problems, because we don't know the properties inside a neutron star. Therefore, lots of equations of state have been proposed during the years, all of them making hypotheses, but we don't really know what's going on in there. And there have been some constraints along the years, and this event, the GW 170817, put another constraint. So the equations of state that do not fit in the region, in this orange region of the plot of the left, are meant to be non-physical. So there are some less candidates to be the good equation of state. For the magnetic field amplification in mergers, there are some processes during and after this merger. For instance, for example, the Kelvin-Helmholtz instability appears when you have a fluid with different velocities, and at the layers where they merge, it is formed some eddies, and these eddies can increase the magnetic field. And this process is more effective at small scales. But nowadays, it is not resolvable because you have to go to scales that are meters or even below meters. On the other hand, there are other processes like the winding and the magnetorotational instability that acts at large scales. And it seems that to produce a jet that comes from that gives the shock gamma reversed that appear during the merger, it seems that a strong magnetic field is needed. So it is believed to have a huge magnetic field in order to have a shock gamma reversed. So with this huge information that this event brings to us, you can try to reproduce it via binary neutron star merger simulations. For instance, some work have been done in the last years. Kyochi, for example, has a work with high-resolution general relativity magneto hydrodynamics simulations of binary neutron star mergers. I have to say that he has the highest resolution simulation ever made, which I present you at the top left of these slides, which has a resolution of only 17 meters. And knowing that the radius of a neutron star is roughly 12 kilometers, they described the star with around 2.5 billion points. At these plots, the below one is another simulation with little less resolution, only 37 meters, and it is represented the magnetic field. We can see that at 3 milliseconds, more or less, after the merger, there's a magnetic amplification that only rises at a high resolution case. So we can conclude that the magnetic amplification is a scale depending problem. There is some amplification at small scales, and then the MRI and the winding appears to form a large scale magnetic field. The problem with these simulations is that they set a huge initial dipolar magnetic field of about 10 to the 15 Gauss in order to solve the MRI. And we know that the neutron stars do not have that high magnetic field initially. Other simulations that have been performed by Cholfi are ones that last over 200 milliseconds after the merger. Here what I present is that if you see this small ball at the center of each plot is the remnant, is the remnant that is after the merger, that appears after the merger, and the lines are the magnetic field. The problem there is that the remnant did not collapse. The jet is formed, but it is not powerful enough to provide a shock gamma reversed. So, as we have seen, the magnetic amplification is something that is a scale-dependent problem. So maybe we have to have a large magnetic field at large scales. But we have seen from Kiyuchi that the transfer energy between kinetic and magnetic at large scales is not as effective as we want. Here in this graphic, I represent you the larger scales that are at the top, the big bubbles at the top, and the small scales at the bottom. The transfer energy between kinetic and magnetic at larger scales is not so effective, but maybe it can be solved if we could solve the Kelvin-Helmholtz instability. For instance, in the Kelvin-Helmholtz instability, when two fluids merge, at the layers they form some eddies. So you can have an energy transfer from the larger scales to the small scales, which is called a cascade, which would be this of here. Then if the fluid is magnetized, when you have an increase of the velocity of the eddies, you can have a dynamo effect. So the kinetic energy is transferred to the magnetic energy, but only at small scales. And then there has to be some mechanism to transfer energy from the small scales to the larger scales of the magnetic energy, which is called an inverse magnetic cascade. So how can we do that? Well, we can try to solve all the scales. There are some ways, and one way is to solve all the scales. So you have a problem at larger scales, and you solve all of them up to the scale that you want by direct numerical simulation. The problem is that it costs lots of computational resources. For instance, the simulations of Kiyuchi, the highest resolution simulation of about 17 meters only, lasts millions of computational time. And the amplification mechanism is still not resolved. So by increasing the resolution will result in an increase of the computational resources by an order of 8 or 10. So maybe it's not the best way. Another way is to perform large area simulations. For instance, you take your problem in the larger scales and simulate up to some scale. And then you model the small scales. It's like applying a special filter to the variables. You can see it more clearly in these plots. Imagine that you have the original resolution, which would be this f, this function f, and then you filter it. By filtering, which would be this f bar, by filtering, you are losing some information, and this information is lost in the subfilter scale. You are committing an error, which is this f prime. But this f bar, this filter resolution, can be computed from a kernel, from an integral of the kernel times the original function. But how it is applied in the nonlinear evolution equations? For instance, if you take the simplest nonlinear evolution equation, which is the Balears, and you apply the filtering, you would have the filtering of u and the filtering of the squared of u. But the filtering of the squared of u is something that you don't know. What you want to evolve is u, not u squared. So this can be solved by a simple trick, which is defining a tau, which is a tensor, that is defined as the difference between the square of the filtered value minus the filtered of the squared value. So now you can have the original equation in terms of something that we know. But another term has appeared. And this new term, this new subfilter scale tensor, by definition, it is not known. So it has to be modeled. In this case, we will talk about explicit subgrid scale models, or just ignored, which in this case, we will talk about implicit large array simulations, in which we do not have any control of it. But we want to model it. So how do we model them as a function of the known filtered values? For instance, by maintaining simulations, the finite resolution of a simulation can be thought as a filter of the conserved equations. And what we have focused on is to perform a subgrid scale modeling, which is called the gradient model. For instance, for mathematical convenience, this f bar that is defined as the integral of the kernel function times the original function, this kernel is assumed to be Gaussian because we want it to be smooth enough to perform an inverse Fourier transform, and then expand it in series of this chi, with this chi being the width of the Gaussian. By doing this, we can express the functions in terms of gradients of the filtered function. So now, if we expand this equation in up to first order interior series, if we expand the Gaussian filter of the Fourier space, we can rewrite the filter of a product of the fields that a priori we don't know into something that we know, which is the product of every filtered field plus the gradient of the fields, multiplied by a constant, which is this chi, which goes as delta squared, where delta is the cell of the grid. We have to say that in the continuous limit, these new terms vanish by construction, because in the continuous limit, this delta tends to 0. Well then, we have performed some simulations by using the Symphony Platform, which is a platform that has been developed by the ICE-CSIC here in Palma, which is public, and uses high order accuracy methods and can solve any evolution equation time dependent, and has an adaptive refinement with parallelization by sampling. For instance, we have done we have applied the gradient model for compressible magneto-hydrodynamics equations, which are the ones that appear at in the red box. And by applying the filtering, we obtain these taus, these subfilter scale terms that a priori we don't know, that appear in the blue box. And then by applying the subgrid scale model, the gradient model one, we obtain this set of expressions for these subgrid scale tensors. Since it is since the amplification of the magnetic field is a scale-dependent problem, we perform some tests of of box simulations to reproduce the Kelvin-Helmholtz instability. Here, what I show you at the top are snapshots of a simulation in which we have two fluids going with different velocities, and at which at some point in the layers they form some eddies, and then the turbulence is developed. At different times, we see at these plots of below, where I represent the energy spectra in front of the wave number. Here I present some simulations with different resolutions. The solid line corresponds to the kinetic energy spectra, and the dashed one corresponds to the magnetic energy spectra. And we see that by increasing the resolution, we obtain more magnetic energy spectra, as expected. And then what we can do is to activate the subgrid scale terms, perform some simulations with these subgrid scale terms that we have computed. And we do this activating them only in low resolution simulations. Something I have to say is that by applying the subgrid scale model, you still have a free parameter, which we will call C, that in principle, it has to be 1. But probably due to the numerical dissipation of the scheme, we have to use large values of this free parameter. At the left, I show you the magnetic energy in front of time. And we see that for a value of C equal to 16, for a resolution of only 250 points in the same box simulations, we obtain a magnetic field amplification of about 1 order of magnitude, comparable with the simulation of the 500 points. And by comparing them, these new simulations with the subgrid scale terms, comparing them in the spectra energy, we see that the behavior of the magnetic energy spectra is the same as if we are doing simulations of about 2000 points of resolution. So with these subgrid scale terms, we have improved our simulations by a factor of 8. So we are obtaining the same behavior as a high resolution simulation with much less resolution. And now that we know how it works with the classical case, we can go to the special relativistic Magneto hydrodynamics. This is a huge work done by Carrasco, which is a member of the group, and the expressions for the subgrid scale terms in the gradient model are some kind of monstrous. So I will only say that here at the top left you have the evolution equations, the new evolution equations, with these definitions at the right, at the top right, in which we can see that everything is mixed. For instance, the Lorentz factor appears everywhere. So when applying the subgrid scale tensors with a gradient model, then you have these other expressions with these taus that are defined with some expressions that, well, maybe it's better not to go into detail. And for general relativistic Magneto hydrodynamics, we have to do some assumptions. The first one is that the spacetime metric, we consider it as non-turbulent. This is that the gradient terms that arise from the magnetic components in the fluid equations are neglected. Then, in the same way, the subgrid scale terms that arise in the Einstein equations are not included. This is that the derivatives of the magnetic hydrodynamic fields are the ones that dominate the nonlinearity of the turbulence. Something that I have to say is that the subgrid scale modeling only mimics the dynamics down to finite depths inside the cell. This means that if new physics appear down to this resolution, we will not see them because there's nothing that we can do. And finally, the violation of the conservation laws by adding these subgrid scale terms is negligible, because it's the same that happens when discretizing the 3+1 equations with a certain numerical scheme. And we have seen that in the continuous limit, these new subgrid scale terms disappear. So with those assumptions in mind, the set of evolution equations look quite similar to the special relativistic case, in which these tensors are defined as these ones at the right. And by performing some box simulations in order to solve the Kelvin-Helmholtz instability, we again find good results for a variety of fixed space-time backgrounds. And finally, for the binary neutron-star mergers, I will show you some numerical methods that we have considered. For instance, we have used the Einstein equations with 5-order accurate finite differences with a Kreiz-Oligarch 6-order dissipation. The reconstruction of the scheme for the fluid is the NP5 with Lax-Friedrichs flux splitting formula. We use a 4th-order differential operators for the subgrid scale terms. And for the time, we use a 4th-order Runge-Kutta. And for the physical setup, we use the conformal covariant Z4 formulation of the Einstein equations. The initial data is given by the Lorentz code, and we set two neutron stars with equal masses up to 1.3 solar masses in quasi-circular orbits separated by 37 kilometers. The magnetic field of each star is about 10 to the 11 Gauss and is confined to each star. And by the equation of state, we use a hybrid with a piecewise polytropic equation, a slide one for the cold part, and an ideal gas for the hot part. And with all of this, we perform some simulations, first without activating the subgrid scale terms, which we will call the low resolution, intermediate resolution, and high resolution simulations, with a resolution of 147 meters for the lower resolution case up to 37 meters for the high resolution one. And then we perform simulations in the low resolution case by activating some of the subgrid scale terms. For instance, we activate the free parameter that appears at the induction equation up to 8, and then we vary the other ones from 0 to 8. Here, what I show you is the slices of the orbital plane for the simulations, for the different simulations that we have done. From top to bottom, there are the low resolution, the intermediate resolution, and the high resolution. And from left to right, it is shown the merger at 2.5, 5, and 10 milliseconds after the merger. The central part, which is colored by green, yellow, and red, is the rest mass density of the remnant, and the orange part is the magnetic field. We can see again that with more resolution, we obtain more magnetic field amplification. For instance, we have started with a magnetic field of about 10 to the 11 Gauss, and we end up in the high resolution simulation with a magnetic field up to the 10 to the 17 Gauss, which is 6 orders of magnitude higher. And focusing on the high resolution simulation, for instance, we can see that in the first 10 milliseconds, the poloidal and the toroidal components of the magnetic field look similar. But at the end, at 10 milliseconds, we can see that the toroidal component is starting to be ordered. Here you can see it in the slices that I show you here. And this is something that we can see more clearly if we take a look at the energy spectra. For instance, I show you only the magnetic energy spectra for the cases that I have shown you before, for the low resolution simulation, the intermediate, and the high resolution one. And we see that the solid line corresponds to the magnetic component, to the poloidal component of the magnetic field, and the dashed one corresponds to the toroidal component of the magnetic field. The left one is the plot at 5 milliseconds after the merger, and the right one corresponds to the 10 milliseconds after the merger. And we see there that the toroidal component of the magnetic field for the high resolution simulation is slightly higher than the poloidal one. So maybe the winding process starts to appear. And then we have seen this, we can perform some simulations in the low resolution case by activating the subgrid scale terms. And here I show you the same plots as before, but adding the low resolution with the subgrid scale terms, but only activating the induction term that appears in the subgrid scale terms. And we see that at 5 milliseconds after the merger, the plot is nearly comparable to the intermediate resolution case, but it seems not in the 10 milliseconds after the merger. This is something that we can see if you plot the magnetic energy in front of time, and we see that the effectiveness of the subgrid scale terms is more evident in the fast amplification phase, which is up to 5 milliseconds after the merger. But we see that by increasing the other three parameters of the subgrid scale terms, the collapse to a black hole starts earlier. The magnetic energy in the CM8 case, which is the resolution with only activating the induction subgrid scale terms, seems to be the same or comparable at 5 milliseconds after the merger. And something that we can see is that by comparing the energy spectra again of the simulations without the subgrid scale terms, and comparing them with simulations with the subgrid scale terms, we see that the increase of the magnetic field of the magnetic energy spectra is equivalent to the magnetic energy spectra of the intermediate simulation, of the intermediate resolution simulation case. So at 5 milliseconds, the effective resolution by using the subgrid scale gradient model is raised by a factor of 2. So we have found that our best results require high values for the induction free parameter that appears in the induction equation of the subgrid scale terms, and 0 or low values for the other ones. Otherwise, the turbulence is suppressed. But this is something that we don't know how it happens, so it needs to be more investigated. And for future work, the simulations that we have performed last until 20 or 20 milliseconds after the merger. But in order to see the MRI and the winding, we will perform long large eddy simulations, which will last more or less 200 milliseconds after the merger. And in conclusion, the turbulent magnetohydrodynamics in binary neutron stars cannot be fully captured in the near future because it costs lots of computational resources. And the magnetic configuration in a post-merger phase is turbulent. We have seen that setting a dipole, that we have set a dipole, and then the magnetic field becomes turbulent and forgets about the initial seed. We have seen that the gradient model allows us to include part of the unresolved dynamics. by saving computational time by an order of magnitude at least. Something that is important is that the formulation, this formulation that we have used, is general, and it can be applied to binary neutron star pulse measures or in any turbulent scenario. And finally, in binary neutron star measures, we have improved the effective resolution of the system by a factor of 2 with the subgrid scale gradient model. And I think that's all. Yeah, that's all. Thank you for your attention. And if you have questions, I will try to answer them.
Okay, thanks a lot, Ricard, for the talk. Is there any question, comment for Ricard? Please just unmute yourself and speak up. Maybe meanwhile we see if there are some other questions. Do you want to comment a little bit more on the project that is extending this? At which stage is it?
Oh, yes. For this project, we have contacted with Cholfi because Cholfi did some simulations that last over 200 milliseconds after the merger. And he has used an equation of state, which is the APR4. And well, maybe by using this equation of state, we can have our simulations last to 200 milliseconds after the measure. But something that is important is that their high resolution simulations is our low resolution simulations. So I don't know if it will last or not, but we will try. And therefore, Carlos Palenzuela has been performing yet some simulations, but until now they haven't arrived to the measuring, but maybe in the next weeks they will.
Yeah, they are very expensive simulation, tens of millions of CPU hours. So they're one simulation.
Yes, okay. The project they have given us the project with I don't know if 47 million hours computation or something like that. But maybe we will use all of them.
Any question? No? Well, if not, I think we can then close this pizza seminar and thank Ricard for the talk. And
thank you, Daniel, for inviting me.
There are no comments, then we can just see each other next week. Okay, I think there are
very much.
Thank you.
You're welcome.
Thank you.